Hi, this is Dr. Bay, and here's Bugsy, and today we're going to go over resonance structures, both their rules and their preferences, so stay tuned.
Organic chemistry,
taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly we fly, give rise to the complexity of life, living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
Let's first review the different types of bonds in ethylene. Recall that ethylene contains 4 sigma CH bonds, 1 sigma CC bond, and 1 pi bond made by the overlap of 2 carbon unhybridized p orbitals. But for today, we're going to be mainly focusing on the role of the unhybridized p orbitals shown in orange. So first, let's identify the hybridization of the carbon and oxygen atoms of ethanoate, which is also known as an acetate ion. So the carbon that's part of the methyl group is sp3 hybridized, since it has 4 bonds connected to it. The carbon in the center contains 1 double bond and 2 single bonds, so it is sp2 hybridized. The oxygen that is double bonded with 2 lone pair electrons is sp2 hybridized, and the oxygen that is single bonded with 3 lone pair of electrons is also sp2 hybridized. Now let's redraw the molecules to show the pi electrons within each p orbital. Remember that unhybridized p orbitals do not exist for sp3 hybridized atoms, so we're going to ignore the methyl group for the time being. So for each sp2 hybridized atom, that being the central carbon and both oxygen atoms, they each have a p orbital shown in orange that is drawn orthogonally or perpendicular to the plane of the molecule. For the left structure, the CO bond is going to the back and is a double bond, which means 1 pi electron in each atom is being shared to form that pi bond. The other oxygen atom that is single bonded houses both pi electrons in its 1p orbital, which is why it has an extra lone pair of electrons, giving it a formal charge of -1. And the same analysis can be done for the molecule on the right. Because the 3 p orbitals are neighboring to one another, the purple pi electrons can spread across these 3 atoms, a term which is called delocalization. And essentially, this is the essence of why resonance exists within a molecule. And if there are at least 3 p orbitals adjacent to one another, then the molecule is considered conjugated, but we'll get into more detail on that concept later on in the course. For now, you just need to know that for many molecules and ions, there isn't a single Lewis structure that provides a truly accurate representation of the molecule. So because of this, we use multiple Lewis structures to describe the molecule and its resonance. To show the redistribution of pi electrons in a molecule, we use curved arrows. This is a super important concept in organic chemistry, so make sure you fully understand how to draw curved arrows. Always start your arrow from the electron source, often where the negative charge is, and draw it towards the electron sink, often where a positive charge is. Here's an example of how we draw our curved arrows in ethanoate. We start the arrow from the negatively charged oxygen and point it towards its single bond to show the new formation of a double bond. Recall that one bond is made up of 2 electrons. And then a second arrow is drawn from the double bond to the oxygen atom. And the same arrows can be drawn for ethanoate on the right-hand side. Double-headed arrows are used in between each resonance contributor shown in blue. And one way to represent this molecule is by drawing a resonance hybrid, which is a weighted average of contributors. Whichever atoms were sp2 hybridized and participated in the resonance or redistribution of pi electrons is where you'll draw a dotted double bonded line, and then put brackets around the whole molecule with the charge in the upper right-hand corner. This shows that the negative charge is equally distributed among the two oxygen atoms. So why is resonance important? Resonance is caused by the delocalization of pi electrons and leads to two things. One, increased stability since the pi electrons are not strictly held together, and two, planarity because hybridization includes an orthogonal p orbital and sp2 hybridized atoms have a geometry of trigonal planar. Therefore, the molecule is much more rigid. So time to get into the nitty-gritty details of resonance structures because what's chemistry without a set of rules? So rule number 1, maintain the same atoms connected in the same order. Do not break single bonds. Just think to yourself, is this atom sp2 hybridized? If it isn't, don't break it. Does it have pi electrons that I could move? Then yes, you can form another resonance contributor. Rule number 2, obey the rules of covalent bonding. It may seem funny that rule 2 is another rule, but look no further because this is one of the most common mistakes I've seen from students who are attempting to draw what they think is a resonance contributor, but sadly it isn't. So just to refresh your memory on covalent bonding, recall that there are no more than 2 electrons in the valence shell of hydrogen, which means hydrogen can only form one single bond. Elements in the second period can hold up to 8 electrons, and in the third period, with the exception of phosphorus and sulfur, can have up to 12 electrons in their valence shell. And here's a super common mistake. As soon as you see an oxygen with a negative charge, you think, okay, I can push it down to an adjacent bond. But wait, notice that the carbon atom has a hybridization of sp3 since it's already bonded to 4 atoms. So pushing a lone pair to form a double bond would break the rules of covalent bonding for carbon, so do not do that. Instead, if you see a positive charge on the carbon atom, that means it now has a hybridization of sp2. Since that means it has an empty, unhybridized p orbital, pushing down one lone pair of electrons from oxygen down to that carbocation is a-okay. So as you practice drawing resonance structures, there are a few patterns that you'll start to recognize. The first pattern is an allylic lone pair. Allylic positions are one atom away from an alkene, while vinylic positions are the carbons that actually are part of the alkene. So for this pattern, the first curved arrow that you'll draw will go from the lone pair at the allylic position to form a new pi bond. And the second curved arrow will go from the pi bond to form a new lone pair. And do not forget to include formal charges. The second pattern is an allylic carbocation. You're going to draw one curved arrow from the pi bond to form a new pi bond. Don't forget to move the carbocation or positive charge to the other end of the system. The third pattern is a lone pair adjacent to a carbocation, and for this you're going to draw only one arrow from the lone pair to form a new pi bond. The fourth pattern is a pi bond between 2 atoms of differing electronegativity, often seen in carbonyl functional groups as well as CN double bonds. You'll draw one curved arrow from the pi bond up to form a new lone pair of electrons on the electronegative atom. And the fifth pattern is conjugated pi bonds within a ring. The number of arrows will depend on the ring size, but take for example this benzene ring. We can move all 3 pi bonds around the ring to form the following resonance contributor. So just to summarize, resonance structures are a set of 2 or more Lewis structures that collectively describe the movement of pi electrons along adjacent, overlapping p orbitals. And here's a list of the 5 different patterns you may come across when drawing resonance structures. The first pattern being an allylic lone pair, second an allylic carbocation, Third, a lone pair adjacent to a carbocation. Fourth, a pi bond between two atoms of differing electronegativity. And fifth, conjugated pi bonds within a ring.
Organic.